Okay, so we just wrapped up 7.8. Let's go ahead and finish the chapter here. 7.9, offshore wind energy, and the very first shot is actually an onshore. But what they're showing here are very large turbines, and so once you get out into the ocean, it, in a sense, becomes easier to make things very large. It's I mean, what's going to happen? It's going to fall over in the ocean, right? I mean, it's not going to fall over on somebody's house or on a road or
Somebody's farmland.
yeah, and somebody's farmland, exactly. And to some extent, this would be worth looking into. It'd be interesting to see what the actual loads are at the base, because if you've got this thing sitting in several hundred feet of water, the effect of gravity is reduced. I mean, you guys have all jumped in the swimming pool, and it's like a little bit like being weightless. So with less weight on the base, you've reduced the amount of stress. So in that sense, it's sort of easier to go bigger without having to add additional materials that you would if you were onshore. One other thing I want to mention, this is something I learned recently, and I'm surprised I'm not seeing more of them, but I just went to the National Society of Professional Engineers meeting in Seattle, and there was a PE there who just got done serving as an expert witness for a wind farm litigation. And what he was finding is these turbines were failing. These big cracks were forming in the sides. And we were even talking about that earlier when Zoe was in the room here. So let's just imagine the wind is blowing from this direction, right? So I've got this big tower sort of flexing back and forth, back and forth, back and forth. Well, where would you expect the crack to develop? It's going to happen on the front or the back, right? It's going to open up and split. Well, what was interesting about this case, he was seeing cracks on the sides. And when he knew that, you got the prevailing wind, flexing the thing, this way, back and forth, he could not for the life of him figure out why the sides were cracking. Any guesses? It wasn't clear to me at first either, but
It's got to be vibrating somewhat.
it was definitely vibration, but the question is what was causing the vibration? Let me show you, I might be able to find a neat little picture out here online. There's this thing called the Struhal effect, or the Struhal number. And I'm not seeing it. I'm just remembering back in my fluid dynamics textbook from college, there was a neat photograph of a boat from above. Oh, that might be a little bit of one there. This is a little bit. Anyway, okay, so this is a reasonable, it's not showing exactly what I wanted to, but if this is a body flowing through a fluid, or a fluid flowing past a body, in the wake, you'll get these little vortices. And they're just like eddies in the river, right? Let me see if I can find another one. This one shows a little bit, this is maybe a little bit better. What you can see is there's this eddy right here, and then there's this one over here. And what happens, they sort of just take turns. There's a left one, then a right one, then a left one, then a right one. And it was those little eddies sort of, on the backside of the turbine sort of pulling the thing left and right rather than back and forth. And so what they ended up doing is deciding might be able to find this one too. There's it's called a clarifier. there are different names for it. Just this guy right here. So this, this little helical thing, you might see that around smokestacks sometime. It's there just to break up that flow. So in the case of the Struhall effect, it's the result of what's called laminar flow, just sort of slow flow. But if you put something rough in there, and again, it wouldn't necessarily have to be a helically shaped object, it's sort of just easy to take a big strip of metal and weld it up the side in a candy cane style. That takes the flow from laminar to turbulent, and now those little eddies don't form. They're just a bunch of little messy, you know, like turbulent flow. You don't see a pattern to it. Okay. So next time you're designing your turbine, keep that in mind. Yeah. Okay. So again, I did mention buoyancy. In this particular turbine, what you can see, they got a nice big fat center of mass sitting down at the bottom. Looks like a big air chamber right here. So it's just it's a big old weeble wobble floating out there in the middle of the ocean, and it can you know, bob up and down to some extent. You've got the guy wires in here. If the designers did their job right, they've got this thing so that it's not, you know, so rigid that it's going to snap. And they've also got some kind of integrated electrical system so that the electricity flows from the tethering wires down to the grid below. I think it's about time for a new book, because right here it says on page 348, 1,500 megawatts of new offshore wind energy capacity will be fully connected in Europe in 2011. 10 new wind farms totaling 3 gigawatts are currently under construction. We've completed, installed further 19,000 megawatts are fully consented. So that's impressive. Okay, global installed offshore wind energy capacity by country. Yeah, UK and Denmark really leading the charge there. Offshore, I'm curious to see where the German offshore turbines might be. We're probably, yeah, so right way up there, up past the nose. You could probably almost zoom in. Let's just say German wind farms. Offshore. Let's just go to maps and see what happens. Oh, Missoula. Okay, there we go.
There's off their shore.
Love it. Oh wait, let's just go. I want to just see the images. I want to see where these guys are. Oh wait, maybe. Oh, shoot. Getting ahead of myself. Okay, here we go. Yeah, so these are pretty far out there. It's all written in German, which I do not speak. See if we can zoom in a little bit. Any you guys have any German on you? Gennesleit, offshore. Yeah, I'm having trouble too. But here's the scale. We're looking at 50 kilometers. So there's 50, 100. So these things are several. Yeah, they're definitely out there. Lots of cable underground. Sort of come in, but you can sort of see where they converge back on land as part of the grid. pretty impressive. It's some neat engineering. Okay, Denmark, another big player. It does mention one floating, it says, interesting development in Norway, floating 2.3 megawatt turbine. That's the one we just saw there, known as the Hywind project. And they were at 220 meters. Yeah. Yeah, so this guy is way offshore, the Thanet offshore wind farm. World's largest, time of writing, September 12. So the whole thing cost 780 million pounds. That's well over $1 billion. Only took 2 years to construct. That is impressive, that you can actually spend that much money that fast. 100. I bet we can probably see this. Let's look at the Thanet. This will probably be visible from space. I think Wally's even got a picture of it in his office. Yeah.
See, that's pretty cool, just the wind turbines don't bother the wildlife, like the large.
I don't know what all the wildlife implications are, but yeah.
Leave a little tiny tugboat.
So this says that there are 100 turbines total. I don't know if we're seeing all of them there. 1, 2, 3, 4, 5, 6. There's a little packet of 30. This guy, I would believe there's 100 there. Oh, but that's a different one.
You can see in the,
Real estate.
look in the back.
Yeah, I believe there's 100 turbines there. Anyway, so, pretty cool that, the authors of this book actually are that close to such a nice facility. Okay, and then there's several other, it looks like Germany's got huge permitting as of this writing, so they're probably way beyond where they are. I'm looking at table 7.6 right now. Total permitting at 54 gigawatts, and in operation, gosh, only 5%. So the industry is taking off in a huge way. Basically going, it's got 20 times more permits than it does installed. And that was in 2010. We talked a little bit earlier about wind mapping, and this is at 100 meters. So these wind maps have been taken 100 meters above the surface of the water. So we talked a little bit about the fact that as your elevation diminishes, the boundary layer reduces the amount of wind speed right at the boundary. I'm sure as you went up, it would get greater still, but we're looking at speeds on the order of 12 meters per second, 25, 30 miles per hour. What they're not showing here is a wind direction, but all of these horizontal wind turbines, they'll spin to face the wind. Okay, and I think that's just about it for this chapter. So in the summary, we did cover power curves. We went through the physics of how you calculate the energy and power flowing through a turbine. We covered just about every make and model imaginable. We looked at the total amount of wind currently in use. We looked at the total potential. Okay, I think we might have just enough time for me to do a couple little time value of money problems.
Okay.
If you got 10 or 15 minutes to hang out, let's just take a look. I want to do that for this class and also just to get you ready for 214 in the spring. So I am actually going to go into 214. Nice little simple warm-up problem there. He has to like show where and how much you have energy stored, and some people are like, okay, in my breakfast, in my bike tire, in my calculator battery, you know, just all. Week 2. Okay. So there are three, well, I'm sure there are many more, but in any time value of money problem, there are three fundamental ways to count money. One is how much you've got now. One is how much you'll have in the future. And the third is how much you'll have if you slice time up between now and the future. So you'll notice there are only three variables. One is P for present. You know, how much money do I have now? Guys, let me pause this for one quick second. I apologize. Okay, so as I was saying, there are sort of three fundamental ways to count money. One is how much I have now, that's P. One is how much I'll have in the future, that's F. And then the other one is how much I'll have annuitized or sliced up, that's A. The other things to consider are how much you actually have right now or in the future or on an annual basis. And so that little $1,600 amount can be any of those three. The term is how long we're talking about. And then the discount is what the money is worth. And so that means either if you have inflation, it means that $1 now is going to be worth less later. If you have deflation, it's just the opposite. So let's just do one easy little example. Let's say that we have $1,000, and let's just say we're going to go for 1 year, and let's say that we have no interest or very little interest. Okay. So what we see is that in the, let's see, what's the best way to look at this? Present divided by future. Yeah, there's a couple different ways to look at it. Let's just, so this is looking at interest. So if we've got a future value, so let's just look at this first little blank right here. If we have a future value of $1,000 and we're paying this very small interest, actually let's just make this 10%. So we've got $1,000 that we need in the future, and we're going to earn 10%. We need to put $909.09 in right now, and that's how much we'll have in 1 year, right? Here's the same thing in reverse. If we put in $1,000 now in the present, and we have 10% earnings, obviously we'll have 1,100 a year from now. Pretty simple. Okay. This one, since it's only 1 year, it's the same. You know, so, if we take this, and I'll do a different one in a second, same thing, the same. With the future and the annuity, it just means that we're going to put in, if we need $1,000 in, if we've got $1,000 as an annuity 1 year into the future, that's the same as having $1,000 1 year into the future. On this guy, if we put $1,000 in 1 year in the future, it's the same as having $1,000. It's a pretty trivial example. Let's just change this to 2 years now. And the numbers change. So it's a 2-year period. If I need, and again, we've got a 10% rate. If I want to have $1,000 in the future, and I'm going to earn 10%, I'm going to have to put in $826 now in the present. If I put in $1,000 now, in 2 years at 10%, I'll have $1,210. You'll notice that it's $1,210 instead of just $1,200 because that $1,100 earned you an extra $10. Or, sorry, $110. $110. Okay. And so on. This means if you have $1,000 per year, you're going to need to put in $1,730. Let's just make this much smaller, because it should just about double. Right, so this present versus annuity, if you have 0 interest, it's just double the amount. If it's 0 interest, it's just half the amount. Those two make sense, right? I see nods. Okay, perfect. Let's take this back to point 1. Same thing here. If I'm going to have $1,000 in 2 years at 10%, I'm going to have to put in $476 each year. And if I'm going to put in $1,000 a year at 10%, I'm going to have $2,100 in the future. So these numbers have to be put in if you're going to do any kind of capital investment. The fact that those guys were able to build that wind farm in 2 years helped these calculations considerably. Because what happens is someone's like, hey, here's $1 billion. When am I going to start getting it back? Well, we better get on the stick, boys. Hurry up and get the turbines built because this $1 billion is burning a pretty big hole in our pocket. So that's where this type of thing can come in. So what's next on that? Okay, so if you wanted, let me do this. File. I'm not going to have time to go through the whole experiment. Save as, but I am going to save it into courses 102. I'm just going to call this summary for time value. So what you could do with your 2 projects, you could take this whole thing, copy it, stick it down here, paste it, and start doing some analyses. What you're going to want to do here, though, is say something like kilowatt hours per year. And gosh, I don't know, let's just say it's a 1 kilowatt system and you're going for 365, so equals 1,000 times 24 times 365. 1, number, dink, comma, kilowatt hours per year. And then you put in dollars per kilowatt hour. Let's just say 0.10. And now you're going to want to change this format somehow. I'll leave it up to you if you want to use rows or columns. But at some point, you're going to have to put in year 1, year 2, year 3 earnings on down the road, and say this is going to equal your kilowatt hours per year times your dollars per kilowatt hour. Control 1, currency. It's a pretty good change. You're going to make almost $1 million in a year. And then finally, let's just do this. I think I've got time here. Let's just say your system costs $3 million. And let's take this guy and pin that on B15. We'll take this, drag it. Oops. We got to pin them both. Take this, drag it. I don't know what the heck Pi's doing there. So now we can plus, not times. So if we take this, we can then, I'm not going to, oops. Equals that plus that. Okay, so now these numbers don't have any interest rates associated with them, but I think you can see how you can get creative and say, okay, $5 million in 6 years is worth how much money now based on whatever my interest rate is. You know, we're in a situation right now in the U.S. that's pretty unique. I mean, interest rates, federal interest rate's like 0. You know, it's 0.5%. So money doesn't cost much. And that's the federal rate. Obviously, you know, banks need to make money, so they're going to, you know, prime plus whatever, et cetera. But so you can start to play around with that a little bit and see, you know, what's your $3 million cost now? Oh, well, look, it looks like I'm going to break even, you know, somewhere between years 2 and 3, assuming, you know, something, you know, some maintenance doesn't happen or some disaster or whatever. So this is a tool you can use to evaluate 2 different technologies, you know, your geothermal versus your wind, et cetera. And it could be that you're like, gosh, I really have to pick one because I only have enough capital to do one project, not both. So, okay, well, thanks, and we'll see you Thursday.